I'm going to talk about something that's more of a theoretical connection between some of the work that I've been doing in my mathematics PhD with the work that I did in my physics PhD. So here I'm going to talk about power law return times. So this is a key aspect of complex systems, at least the ones that I studied in my physics PhD, and something called the Dani Correspondence principle, something which is quite important in the field of Diophantine approximation, which is the subject of my PhD. I'd like to thank you all for inviting me and for all of the wonderful food and venue to give this talk in. Okay, so first I'm going to give an introduction to exactly what I have in mind to talk about, and then that will require me to talk about the two things I mentioned just now, Diophantine approximation and the Dani correspondence principle. Then there are some preliminary results that I'll talk about and some future work. So as an introduction, I would like to say a little bit about first generally what Diophantine approximation is. It's essentially approximation of typically irrational numbers by rational numbers, and it can be used to find best approximates. These are often useful in explaining approximate recurrences in nearly periodic systems, such as the orbits of planets and things like that. But they're also used in measurement and in principle can be used in compression. I wanted to connect those to power law intermittence, and it turns out that there is a connection through a correspondence between dynamics, a dynamical system. Typically, people use this for ergodic properties. I'm not going to be using it in that aspect, but relating ergodic properties of a certain dynamical system to approximation properties of sets of numbers. And so instead, I'm going to use it the opposite way. I'm going to posit a complex a complex aspect of that dynamical system, a power law return time, and then see what sort of mathematics, what sorts of numbers would be required, or what some traits of those numbers would be, assuming they can be found. Finding them itself is future work. So let me say first what Diophantine approximation is in its most basic form. So in its most basic form, there is a theorem called Liouville's theorem, which essentially quantifies the fact that not only can you find rationals everywhere, essentially on the real line, but you can find them quite often. In fact, you can find the weaker version of this theorem says you can find an approximation if you want to approximate an irrational number alpha by a rational, say p over q. Then you can get within 1 over some constant times q of that number, and this can be proved through an appeal to the pigeonhole principle, essentially splitting up the region between 0 and 1 into q pieces, and noting that once you have q plus 1 multiples of a number, which you get here, then you must have 2 that are within 1 over q of each other. So essentially, this is fairly straightforward to prove, and was noticed in the late 1800s. Somewhat more difficult to prove is this version of it up here, which where q here is a bound on the denominator of your approximate. But I won't spend too much time on Liouville's theorem itself. I just want to introduced this to say what's going on, what it means to approximate things in this context, and to introduce these last two concepts at the bottom. So BA here stands for badly approximable numbers. So there are, in fact, numbers that saturate this bound obviously for a different constant here. And so it turns out that in terms of the rate of approximation, the power that you have, or the function here on the other side of the inequality, there are numbers that are as bad as possible. You can't approximate them any better than the minimum that you get from Liouville's theorem. And there, on the other hand, there are other numbers. So this is actually a relatively small set. This is a set of measure 0 on the real line. So if you throw a dart at the real line, so to speak, you won't hit one of these. On the other hand, there are what are called the very well approximable numbers, and these are the things which you can do much better. You can do quantitatively better in the sense that you can approximate at least as well as a higher power, a strictly higher power than what you get just from Liouville's theorem. And so these are essentially very nice numbers if you're trying to get a very simple representation of them in terms of a rational number. It turns out these are also a relatively small set of the real line. They're also measure 0, but things in between, things that don't have that have a power that really don't go like a power for the approximability on the right hand side. Those are really sort of essentially everything, so to speak, on the real line, and they're part of what I'm going to talk about today. So that's why so the way that what the Dani correspondence is, so the way that people turn an approximation problem into a dynamics problem is to say that, okay, we will take a pair of numbers, a pair of integers, p and q, where q should be non-zero, and we'll apply the following operations to it. So we'll multiply it by this matrix here, which contains the number that we're thinking of approximating, and we'll dilate one direction and shrink the other. And so you might note that these two are both special linear matrices. They both have determinant 1. So the size of the vector is preserved by this in some sense. For any notion of for any norm you want to put on this space, it'll be preserved. And on the right hand side, you see what we have here in the first component. We have exactly up to a sign what we're using here to look at how well you're approximating the irrational number. And in the bottom, we have a way to keep track of how big the denominators are. So how much work you're having to do, how complicated your measuring device has to be in some sense. Now, this is if you fix some p and some q. This is what you'll get. I'm sorry, there should be an exponential factor on each. So this factor should go on here, and this one on there. But anyway, as I said, the size of the vector is invariant. For any particular p and q, you don't actually change this, the norm of the whole vector. On the other hand, if you let p and q range over their entire possible set of values, there will be values of lattice vectors. You can think of this as a lattice. There will be values of these vectors that can be very close to the origin and values that are very far away. Certainly the origin won't be included because q equal to 0 won't be included, and p equal to 0, at least for a large enough q, will not be a good approximation either. So what we find is that the interesting property is the properties of this lattice. under this dynamical system where you're applying this to every element of the lattice. I'm watching the dynamics. So another key piece of information, since I introduced a lattice, is that there are certain geometric properties of lattices that turn out to be essential for understanding the dynamical system. So here, Minkowski's theorem is at least part of this theorem is the simple observation that a point can be at most 2 lattice points apart. If you omit the origin, then the farthest away 2 points can be from each other, and not include a lattice point between them is just the distance between -1 and 1. And so this gives you the fact, if you raise this to the appropriate power here, we're looking at a 2-dimensional matrix. So we raise it to the power 2. So that gives us this upper bound of 4 here. It's a simple observation that gives you an upper bound on the size of the matrix. And this is the only, on the size of the lattice vector. This is the only part that we'll need for the remainder. Minkowski's theorem actually also proves a lower bound as well, which is significantly more difficult and involves working on the successive minima function and linear forms, which I won't go into. So since we have a dynamical system, these lambdas, which are the successive minima of the lattice, the size of the lattice vectors, are going to change with time. And so in particular, I've labeled these in order of size. So lambda 1 here is the smallest size vector in the lattice, and lambda 2 is the next to largest. Next to smallest, which here is also the largest. So we're only going to be interested in lambda 1 here. And in particular, it turns out that because of the way the dynamics works, everything is exponential here. So if we simply take a logarithm, we can make everything linear, which is usually much easier to understand and do calculations on. So it turns out that through some work of a pair of colleagues in Boston University, Dimitri Kleinbach and Margulis, it was possible to relate the properties of this negative of the log of the shortest lattice vector with a Diophantine property with the approximability of the irrational that we're looking at. So here, and I apologize, I'm going to use psi here for 2 completely different things. Here psi is the approximation function that we're looking at. So it's what I've defined down here in the bottom. It's what we, in the first case in Liouville's theorem, or in the weak version of Liouville's theorem, was just some constant divided by q. So it turns out you can define this R of t in this way. So it's implicitly defined through an exponential. And with appropriate restrictions on the class of functions that you can have for this for approximation, you can always get an R of t that corresponds to each psi and vice versa. So what do these typically look like? So delta of t typically looks something like this. So you typically have times where the size of the smallest lattice vector increases for a while. So the orbits are hyperbolic, and part of the orbit, one of the components of the lattice vector will increase in size until it reaches the size of the other component, in which case it would have its minimum size, the minimum size of that it would have, and then it'll begin increasing again. But at some point, other lattice vectors will come in, and they will take over the role of smallest lattice vector. And so the size of the smallest lattice vector will decrease until, again, that the 2 components are of equal size, and then it increases again, and so on and so forth. So a couple of things to note is it's certain that these peaks will get higher because you're getting better and better. Okay. It is, except for one special case, certain that these peaks will get higher, which is why I drew it like this. It's not always certain that these troughs will also get higher, but in many cases that's the case. So that's why I drew it like this. And I've labeled them with variables here, T1, T2, and T3, to correspond to or suggest the idea of times. So that's what I'm going to, this is the way I'm going to make a connection with the theory of complexity, is I'm going to look at the times between the peaks of the function delta of t and ask what happens or what properties of these numbers correspond to inter-peak times that are power law in distribution. 2 minutes. Okay. And so so let me just say really quickly what sorts of power laws I'm talking about. I'm really talking about processes that are renewal. So this just means that those inter-event times, which I've called tau here, are independent and identically distributed. One example would be a Poisson process, but of much more interest is, at least for complexity theorists, is the case when we have a power law for this distribution of times, and in particular in the case where the second and in some cases the first moment doesn't exist. So in those cases, what we have are two key function. Well, one key function that has two different behaviors depending on the power law exponent. So if the power law exponent is very small, so if the tail of the distribution is very wide, so to speak, then the rate of events goes to 0. So here this mu is smaller than 2, so this exponent is negative. So this decreases and asymptotes to 0. And this also it also goes to 0 in the case when mu is equal to 2, typically, at least for the Mandeville map. I mean the Homo-Mandeville distribution, but it doesn't go as a power law. Whereas in the case where the exponent is between 2 and 3, we have a constant. So this represents the fact that the first moment exists, but there's a very slow approach to that equilibrium value. And so this is somewhat more like all the other values of mu larger than 2. And so here's the main connection between the two worlds, so to speak. So going back to the fact that we've sort of defined delta as the shortest lattice vector, and we know from Minkowski's theorem that the shortest lattice vector can't possibly be larger than the largest possible value of the shortest lattice vector, which we saw was 4, or the product, which was 4. Then we have a bound on how small this delta can be. But we know something about, just because of the fact that it's linear in between the peaks. Because of the fact that it's linear, we know that it has to go down, and however much it goes down, it comes back up, and then whatever is left over in the time that there is between two peaks, that's the whole rest of the increase in delta in between the two. And so it turns out that if we know something about this inter-event time, we can get that from the rate of events essentially directly. And so just relating those two, taking into account the fact that we have essentially this relation between tau and the rate, we can get the fact that the product between delta and R of t is more or less constant, at least asymptotically. And so this gives us, and I won't go through the math to flesh out how we get this, but it turns out in the case when mu is smaller than 2, we get not very well approximable numbers. So they go, their ability to be approximated is not any better than any power higher than 1. So you can't approximate them as well as the very well approximable numbers. But they're not badly approximable. They're things of this form. So the function delta of t goes as a power, and this is sorry, this should be r of t here. R of t goes as a power. That actually, in this case, they'd be the same. Whereas in the case where it's badly approximable, it becomes linear in the infinite limit. So in the first case, we have something that is very interesting. It's neither badly approximable nor very well approximable, and it's also corresponding to a region in complexity space that is very interesting, mu smaller than 2, where you have perennial aging. On the other hand, when mu is larger than 2, things are badly approximable, and so this is sort of less interesting from an approximation point of view, and somewhat less interesting also from a complexity point of view. So that's all I had to say, except for some future work, but I should look for particular numbers that satisfy these criteria. It's possible to expand this to higher dimensions, at least on one side of this correspondence. So presumably the other side will work too, and that should be given some thought. And then also, so here I assumed independent and identically distributed inter-event times. There are many other processes of interest to the complexity community where there's correlation between those inter-event times. And so that would be also, I think, of interest. Thank you very much for listening.